grades marked here. In case you're a little confused by my grading system, I just graded out of 3 points. So 3 points is perfect score, you did everything correctly and you turned it in on time and everything like that. 2 points is you had the right idea, I can see where you were going, maybe you had one math error or some little logic error here or there. 1 point is pretty much you didn't do it at all, or you turned it in late and gotten something wrong. So 0 points is you didn't turn it in all, obviously, right? And then I just subtract 1 point if it was late. Now, I don't subtract more points if it's more late, so take your time if you've gone ahead and been late anyways. But that's pretty much my grading scale. It's pretty simple. I like to keep it pretty simple. But yeah, I'm keeping track of all those assignments, so make sure you're turning your stuff in, all right? So assignment 1, if you don't remember, was that math problem that we had on paper. I gave back. Everybody who's already turned it in should have it back. And then the entry ticket from last class as well. Oh, and a little bit of more information that I think might affect our class a little bit. I went ahead and talked to the teachers of the CAD class, and we're gonna try to have them collaborate with us a little bit. So we know we built those little test rigs that we're gonna use to test some simple base motions, but I talked to the CAD class, and since, I mean, technically, if we were on an actual team right now doing something, it would be their job to build us our test rigs as we see fit, right? So we're gonna go ahead and start taking notes whenever we want some kind of test rig, and we're gonna send those notes over to the CAD class, and they're gonna go ahead and design it and then build it for us, cut all the pieces that they need to cut, and hopefully have it ready for us whenever they're done, maybe in a week from when we give them those notes. So we probably won't be spending any more classes building, which is I think good if you ask me, but yeah, that's a little bit of a development. Go ahead and get started. Everybody else can join us later on. Let's hope they don't fall too behind. So, moving on, this is our agenda for today. Remember, our whole theme of the week is abstraction, and I mean that in the idea that we're trying to hide the complexities of our code from the average user, all right? So, to go over that, we have first objects. We're going to continue with that wheel that we started last class. I'm going to start off with a function example and kind of continue on that line of thought. Then we're going to go over the driver station because I think it's about time we started coding some actual robots. So we're going to go over the driver station setup and hopefully configure that plus drive robot that we created before. And then we're going to go over the FTC SDK. So we'll learn a little more about what that is and why we need to know what it is when we're programming these robots. Obviously, I'm going over the package, boilerplate, all that stuff up there. Again, we'll learn more about that when we get there. And then we're going to be going over encoders. So that's going to be hopefully our final lesson of the day. I'm really hoping we get through this whole thing. That would be a very productive session in my eyes. So, moving forward, if you remember, this was our wheel assignment from last class. I didn't have you guys do it at home because I wanted to do it today. So, just another little tidbit. You'll remember I ended off the last class by showing you guys an example of an easy way to do the get driven, right? And the way I did that before was pretty much I was returning the RPM, which is our RPM up here, right? So I was returning RPM multiplied by our gear ratio. So this pretty much does what we're asking it to do. But remember, this get driven RPM function, what we really want to do is give us the final RPM. So what I mean by that is you have your motor, right? And it has the internal gear and then the external gear. And then we can have that connected to any set of gears that we have through this array list up here. So if we want to get the final gear ratio, or the final RPM from that whole big gear ratio, right? We actually have to multiply it by all of the gear ratios stored within this list. So the way I did that was first I created my function to add an external gear. So I just called it add X gear. And remember, we first have to give it some kind of return type. So in this case, since I'm just adding to a list, I'm gonna give it void because it doesn't really need to return anything. And in here, the code is pretty simple. I'm gonna take an input of the gear ratio. So I could say double and then gear ratio. And then down here, I return, or I add to my list that gear ratio. So I say external gear ratios dot add, and then whatever I want to add. So in this case, it's gr. Remember, we have a gr up here, but unless I say this dot gr, it's going to assume I mean the input. So in this case, it's going to assume that's the input, and that's pretty much all you need to do, right? Very simple. Now, there's another way I could do this. Maybe I wanted the user to, instead of inputting the gear ratios as a decimal, right, or as like that divided out fraction, I want them to just input one set of teeth and then the other set of teeth, right? So the way I would do that is here I could say int driver teeth, and we have to make it an actual variable name. And then here I'd say int driven teeth. Now my names are pretty self-explanatory, so I don't think I have to explain what each one is. And then here I would add driver teeth divided by driven teeth. Now, I want us to kind of pause and look at this for a second because there's two things that this code needs. A little bit more thought, because when I'm adding driver teeth over driven teeth, this is obviously a gear ratio, right? From driver to driven, but these gear ratios I'm planning on using later for a very specific purpose, correct? I'm using them to calculate my RPM. So when I add these gear ratios, I want to add them in a way that'll make it easiest to calculate RPM. Now, the reason I'm saying this is because there's two things that are affected by my gear ratios, right? The torque and the speed, and they're affected inversely. So the speed goes up and the torque goes down, and vice versa, right? So if I was trying to calculate torque, I would want these two at a certain order. And if it was calculating speed, I would want to calculate them in a different order, right? So you can kind of see what I mean by this. If I'm calculating RPM, right? I have my RPM of the driver connected to some gear, and then I have my driven gear. Now we know the RPM right here, let's say is X, so it's X revolutions per minute. Now to convert that to the revolutions here, on the top, I have to leave the revolutions of this outer gear. So I'm gonna say outer rev. And on the bottom is gonna be the inner revolutions, so just rev. Now remember, we do it this way, that way so that we can cancel out these two units. And then when we multiply across, we have X outer revolutions per minute. So our new RPM, but in outer revolutions instead of the rev or the inner revolutions, right? So you can see here, the ratio that I'm using is outer revolutions over revolutions. Now, up here, I'm calling for the input of the driver teeth and the driven teeth. So basically, I want to represent this ratio as driver teeth to driven teeth in some way. So it's either going to be driver teeth over driven teeth or driven teeth over driver teeth. But I need to figure out which one of those is the same as this ratio right here. That make sense? So I'll give y'all a couple minutes to think it through before I give you the answer. Just pen and paper or on your computers or whatever you need to do. So basically, if you're confused, the math or the logic kind of goes as so. We have 2 gears, right? Let's say this is our driver and it has 40 teeth, and this is our driven and it has 80 teeth. When this one turns twice, right? This one turns twice. This one is going to turn once. And remember, you can think of it like those 40 teeth are pushing 40 of these teeth, right? So we have to do that twice for this to take 1 for full revolution. So you can see these are kind of the revolutions that would go here, right? This revolves twice as this revolves once. So in that case, it would be 2 over 1 here, which is basically saying the driver over the driven, right? Or, sorry, outer over inner, so it would be the 1 over 2. So the opposite of what I just said, right? So 1 over 2, up top this 1 is going to be the driven over the driver. Now you can see this 1/2 is the same, again, as the ratio of driven to driver. So the driven, actually, the little bit of the reverse, it would be driven on the bottom and driver on the top. Now, gonna re-explain it because I got a few things wrong as I was going. So pretty much this ratio right here, on top, you have your outer revolutions or the driven revolutions, right? On the bottom, you have the revolutions taken by your inner one or your driver. So right here, we figured out what those actual things were. So 2 times and 1 time. 2 times is for the driver, 1 time for the driven. So we went ahead and put that in an actual fraction. And remember, we got which one goes on top and bottom based on the thing we're trying to match. So we put the outer gear or the driven on top. So that's the 1. And then we put the driver, which is right here, the inner gear. We took the 2 from that, so we got 1/2. So to replicate that 1/2, we have to do driver over driven, because 40 divided by 80 is 1/2. Y'all see how I got from here to here? So this is 1/2. I have to replicate that by some ratio of these 2 teeth. So we look at that, that's 1/2. To get 1/2 from 40 and 80, we put a 40 over 80, and that is 1/2, 40 divided by 80. Right. Where? It flips. Pretty much, the thing you'll find is anytime you're doing RPM calculations, RPM is gonna be speed, right? So remember, speed and torque are gonna be inverse. So if you wanted to just follow exactly what this was, that would help you calculate torque. So if I was looking for the torque, I would just do driven over driver, right? I would just do outer rev over inner rev. That would get me straight to my answer. But since I'm looking for speed, I have to flip it. So it's all about ratios. It gets easier the more you do it. But for now, all that calculation basically led me to say, instead of doing driver over driven, I'm gonna do driven over driver. So here, just gonna change that. And ta-da, that's gonna make my code easier. So I'm getting an error here. This is the second thing that I was mentioning that we have to look at with this code. Basically, the problem is I have 2 integers here, right? Driver teeth, which I assumed would be an integer because you can't have half a tooth on a gear. And if you do, you should probably replace that gear. And again, another integer for the driven teeth. So when I divide 2 integers, the result is an integer. And this external gears, remember, holds doubles because it's gear ratios. So to do this properly, I have to convert this to a double. And the way we do that is we put the type that we want to convert it in parentheses, and then we put it to the left of whatever we want to convert. So basically this is converting this variable to a double. And now what's happening is I'm dividing a double by an integer, which is going to give me a double and double. So that is another way that you could do it. Personally, I found my way easier, but this does kind of aid that little abstraction idea that we're doing, right? We're hiding the complexities of our code, so if the user has their code in a way where they're getting the actual teeth, now they don't have to do the calculations themselves to find the gear ratio and then add that gear ratio. That make sense? So that's that function. Now we've added a gear ratio. Now I want to implement these gear ratios to my get driven RPM, and we actually made it really simple for ourselves. All I'm going to do is I'm going to say double D RPM of the driven, and I'm going to set it to RPM times gear ratio. So right here, RPM is the inner motor RPM, and gear ratio is the gear ratio of the motor itself. And then down here, I'm basically just going to write a loop to loop through all of the items inside of external gear ratios, and I'm going to multiply my RPM by those. So here I'm just going to say double I, and I'm saying double I is for index, right? So it's going to be my index, which is going to travel through my whole list. And since the list contains doubles, I'm making it a double. And then you do a colon, and then external gears. And this will basically set I to a value within external gears for every iteration, and then push I one forward every single time we go forward in that loop. So here, I'm going to say driven RPM times equals I. And then at the end here, instead of returning this, I'm going to return the new RPM that I calculated. And it's mad at me because I said this was going to be an integer, but I lied, this is a double. So we change it to a double, and ta-da, we have our now driven RPM. Now, the reason, again, it's so easy because we know all of the values within this array are already prepped to be done for this calculation. So we've already made them all in this form where we can just multiply it by our RPM to get the new RPM of that gear. So you can kind of think of this like the first iteration is going to multiply it and give me the RPM of the gear right here. And then the second iteration is going to give me the next gear, and then the next gear, and then the next gear, all the way until we get to the actual wheel. So that's that function. I know y'all have a whole bunch more to go over, so y'all can go ahead and get started on those. We're going to finish going over, or we're going to be done with this assignment, I'd say at 7:30, so we can hopefully have time to move on with everything else. Y'all can go ahead and get started. I know a couple of you already finished this, so in the meantime, I would love if you go around, help your peers. Remember, this is a collaborative space, so we only move on when everybody's good to go. Okay, y'all can get to work. Does anybody have any questions or not understand what they're supposed to be going over right now or doing right now? I know that was a little bit confusing, the demonstration, so let me know. Go ahead. Maybe you shouldn't be late. No, I'm messing. Jumana actually could, I'm sure, fill you in on what's going on. Remember, collaborative space, everybody, collaboration. Yeah, we're just gonna do it. Okay, so next is the driver station stuff. So I have one right here that y'all can pass around. The first lesson that you will learn about the driver hub is that they are always dead. So the one that you're passing around right now, it was alive at the beginning of this class, it's dead now. It is unfortunate, but y'all can pass it around if you you haven't used one ever, and you just kind of want to see what they look like. But pretty much, the driver station is a little piece of technology that we use to communicate with the robot over Wi-Fi direct. So every time you open up one of these robots, and you can see if you stand up, I have Plus Drive right here booted up and turned on and everything like that. Every single time you see these flashing lights, every single time you see this green, that means you have a Wi-Fi direct signal booted up, and basically we connect to that Wi-Fi with our driver hub. Now I have one plugged in up here. Thank you so much. I have one plugged in up here. It doesn't have a battery, so I cannot pass it around. So it's gonna stay plugged in, but I'm kind of gonna use it to demonstrate how we can configure our robots. Now I know many of you probably know this is extremely easy to do, but we have to go over it because I know some people don't know how to configure robots, and obviously it's really important. So I have mine booted up right now. You can kind of see, I know it's very small. I'm gonna kind of use this one to kind of demonstrate where I'm going. I open up the driver station app. So this right here, where you see on your screen, this is opened up to the driver station app. It's just an app that's downloaded on every single one of these devices. You open that up, and you're gonna see this little display with a bunch of different things that you can look at, such as the driver station battery, which is just the battery of the device itself. Right here is the battery that's connected to the robot, the voltage that it's at. It's going to range from around 12 volts to around 14 volts. You can go over, you can go below, but that'll tell you what battery your robot's at, how much you have left. And then this additional menu is actually where we're going to go when we want to configure a robot. So y'all can come closer if you like. I went ahead and clicked on that additional menu and clicked on configure robot, and it pulls up this little menu right here. Again, this is very easy, so I'm kind of going to speed run this process. You basically hit new to create a configuration, and it's going to show you a bunch of different areas that you can go to that correspond to areas on your robot where you have wires plugged in. So for example, it says expansion hub and control hub. Those are two little sections that you can go to, right? So if I go to expansion hub, it's going to say motors, servos, digital devices, all of those ports that we went over, I believe a week ago, maybe a week and a half ago. And it's going to have numbers for each of those ports, 0, 1, 2, 3, just like these ports are numbered, right? So basically all you're going to do is in each of those sections, you can kind of see right here, or can't kind of see because it's really small. I have a drop-down menu for what type of motor it is. So for example, for Plus Drive, on port 0, I have a Never Rest motor, or a Go Build a Yellow Jacket. So I would find the Go Build a Yellow Jacket motor and click on it, and then I have to give it a name. Now that name is going to be important, and we're going to show that to you when we go over the actual programming stuff here right now. So the other two things that you need to note from this menu are teleop menus and autonomous menus. We're going to go over how to navigate those in a minute, but pretty much autonomous and teleop are going to be two different types of modes that our robot can be in, all right? So, going over the FTC SDK, remember I said we were going to get to this later. This is kind of the bulk of what we're doing today. Basically, the first program has written a whole bunch of code to make it easier for us to interact with the hardware and electronics of this robot. Now, hint, hint, abstraction, right? Remember, abstraction is the idea of hiding the complexities of our code. So, FTC has hidden the complexities of code behind their own SDK, and now we can use all of their stuff without knowing exactly how they work, right? And I'm going to show you those in a minute. So the two things we're going to focus on today are the gamepad interactions and the DC motor class. Now, I'm going to go real quick to get the gamepad because we're going to need that in a moment, so I'll be right back. No, I am quite speedy. So this is a gamepad. In case you haven't used one before, I'm sure most of you have, or have at least seen it before. Now it has two types of inputs. Remember, we went over this when we were going over the different types of ports that the motor had, or that the control hub had, right? So these two types of inputs are digital and analog inputs. Can anybody remind me what digital means? Go ahead. Pretty much, yeah. So digital is going to be another word for discrete. In other words, it has a discrete amount of values, or a set amount of values that it can return. So in terms of this gamepad, The digital inputs are going to be things like buttons, right? So for example, all the A, B, X, Y buttons, they only have two possible values, right? They're either pressed or unpressed. So it's a digital input. The other type of input is analog, so it can either give you, or it can give you any input within a range. So the analog inputs that you're going to find on this controller are the triggers and the two joysticks. So the two joysticks actually have two analog inputs each for the X and Y axes, respectively. And the joysticks are going to return for each input. It's going to be from -1 to 1. So anything in between -1 and 1, it can return. And then the triggers are going to be anything from 0 to 1. So if you push the trigger halfway, it'll give you 0.5, right? So I'm going to give you guys this controller to, again, pass around and kind of familiarize yourself with the different kinds of buttons. I'm not going to go over every single one because, again, all of them work pretty much in one of those two ways. Now, what's really more worth going over is how we code each of these buttons. So, right here I have my Android Studio, right? But this is just an empty Java project. So if I wanted to code for things on this robot, I have to use the FTC SDK, right? So basically this is a package. And I don't know if we've gone over packages before, but it's essentially a full stack of Java and other language programs that all come together to make whatever it is that I'm doing work, right? So remember, we can make multiple files in Java, right, and have them all work together. Now this is a whole project of files. So there's, in here, I'm gonna find tons and tons of files that I am pretty much either never going to use or only gonna use very rarely, but all this stuff I did not write, right? This belongs to the FTC SDK, and you can get this from online. So if any of you look up FTC SDK, you'll find a GitHub page, right? If we're not familiar with GitHub, basically it's an online resource where we can store our code. So you'll find literally this entire exact project on GitHub, aside from any classes that I make myself. So I'm gonna go ahead and just make a little test class. To do that, we always operate within this org.firstinspires.ftc.teamcode file when we're within the SDK. So what I'm going to do is I'm going to go ahead and create a new Java class, not what I just clicked. And here this is going to look pretty much like all of the other classes that we've created. So it's going to ask me to add it to Git. Remember, we're going to use GitHub later, but we don't have to worry about that right now, so I'm just going to say no. And here you can see this pretty much opens up to exactly what I've had in all of my projects before. We have one specific line that's probably not on your online compilers. It's this package. So basically this is telling you where within the project I am. So I have to have this in every file. It'll probably automatically make it for you, whether you're using Android Studio or on Java, but just know that if this file is wrong, a lot of your code is gonna crap out and it's not gonna be very happy with you. So this right here is, again, just the file we're working within. So org.firstinspires.ftc.teamcode. If I had another folder that I was working within, it would say that folder's name instead. So right here, I have my public class test. Remember, if it's a public class, it has to have the same name as the file. So here it's public class test because I'm in test.java. So to make a program that runs on this robot, I have to do a couple things. This is called the boilerplate of the SDK, right? Remember, boilerplate is the basic commands that you have to do to get a program to run the way you want it to. So the boilerplate for this specific instance, when we're creating a program that we want our robot to run, is going to be extends linear op mode, and that's right after this class part, and it's going to get mad at me because I do have to import this, I do believe. I can see that actually, thank you. We're going to get, oh, is it a typo? Oh yeah, there we go. All right, fix that one, and it's going to tell me I have to import it right now, or maybe not. There we go. So now this is basically saying, we're going to go over inheritance and polymorphism later, but to kind of give it the short the short explanation, right? We have classes, right, that we can create. Now, sometimes I want to change the properties of a certain class without changing that class, right? Let's say I have this class and I'm creating 3 objects out of it, but then I have this 4th object that I want to make that's slightly different. It needs slightly different functions, but it can still use the rest of that class. What I'm going to do is I'm going to use the concept of inheritance. So by saying extends linear op mode, it's inheriting all of the properties of the linear op mode class. So I can actually go, I hit control click just now, so that basically takes me to wherever the file for linear op mode is. But you can see this is literally just a class that somebody else created that does whatever all the stuff that I need it to do, right? So it has all of the different things, and we'll learn about the different things that linear op mode gives us. But you can see I'm basically taking this class, I'm saying all of its properties I want to be inherited to this class. So later on you're going to see me reference variables and different objects and stuff like that without having declared them. They are going to come from this linear op mode class, all right? So I said extends linear op mode, but you can see it's throwing me an error right now, and the reason is when I extend linear op mode, they've specified this within the code of linear op mode, right? I have to either declare it as abstract or implement the abstract method run op mode. So I'm going to go ahead and do the latter because that's how we do it. It's public void run op mode. And basically this is the function that's actually going to run when this class plays. Oh Lord. There we go. And run op mode takes in no inputs. And I'm going to go ahead and open that up. So now I'm getting no errors. So basically what's happening in this class is it's a regular Java class, just like any other one, right? I'm going to be able to create variables up here if I want. I can set them to a value. I can change that value later on. And the properties of scope still apply. So anything that I create up here, I can use down here. Anything that I create down here, I cannot use up here or down here, right? So I can change that number if I wanted to. Everything pretty much normal. But what's gonna happen is I'm gonna be able to find this linear op mode on my driver hub. Remember, we have that, there it is, our drop-down menus here for autonomous and teleops. Now I'm going to be able to find linear op mode either on the teleop side or the autonomous side and play it to my robot. And it'll play whatever code I have. Now, right now, my code is going to do absolutely nothing because I've written in 2 very useless lines, but the FTC SDK allows us to do a lot more. So let's say I wanted to interact with one of my motors, right? What I do is I use the DC motor class. So it'll be DC motor. I'm creating a DC motor object, right? This is why we went over objects, because we're going to use them all the time. So it'll be DC motor. I give it a name, say motor equals new DC motor. And here, this takes in a very specific type of argument. Now, that argument is not available out here, all right? So these are things you're just gonna have to learn about the SDK. They're less about Java specifically and more about this is how FTC does it. So this section of this argument is not available until after this run op mode point. So what I'm going to do instead is I'm just going to declare motor and I'm going to leave it as null. There we go. And then down here, I can define it. Now, what do we define our motor object to? It is what we hardware mapped it as. So in here, it's going to be hardware map dot get, and in here it's going to be DC motor dot class, and the name of whatever you named it. So remember, I said you put in what you want to name the motor whenever you're inside of your configuration. So here you're just going to put whatever you put in there. So it'll be motor or whatever you put. So that's the essentials of how you define a motor. And actually, my apologies, you don't actually have to do the new DC motor part because hardwaremap.get returns a DC motor. All right, so this function returns a DC motor or a class based on what you put right here. So basically, it'll just replace this with the DC motor class that we need. That is mapped to whatever we set in our configuration. All to say that this basically lets us use our motor now. So right after this point, we can now use our motor with whatever functions we want. And again, those functions are part of the SDK. So the basic function that we're going over right now is set power. Now this function takes in a number anywhere from -1 to 1. And basically all it does is it pushes power proportional to the percentage that you gave it. So this is a percentage, right? If I say 0.5, that'll be 50%. If I say -0.5, that'll be -50%. 1 would be 100%, -1 would be -100%. 0 would be 0%. So it pushes power proportional to that percent that you gave it to the motor and starts driving it. So if I put this line right here, what'll happen is once I start my program, it'll set power and it'll send 50% power to said motor. It'll start going and then my program will end immediately, right? But that's pretty much how we're going to interact with motors. So what I'm gonna do is I'm actually gonna have you guys pull up, here, we're gonna do a random number generation, generator, and we're gonna pull up on one of your computers on Java, that way we can start coding this robot up. So, actually, we don't have all of our numbers. What is the largest number that we have here? You don't know? I believe, Dimash, what's your number? 9? I believe 11 is over here, right? So we'll just go from 11. Number generator. We don't have number 1, do we? Oh, you're number 1? Fantastic. Okay, so go ahead and pull up on your computer. What you're gonna do is pull up. So the first thing you need to do is connect to the Wi-Fi of the robot. Now this Wi-Fi is called, let's see. So all we're doing right now is pulling up the code, or pulling up a different like IDE or area to code, so we can connect to this robot, push code, and then actually see something work instead of just watching me type on the screen. But this Wi-Fi, I believe, is called SOS. So on your computer, you're just going to connect to SOS. Huh? What do you mean option? Yeah, let me see. Is supposed to be somewhere in this list. Our battery is dying. Okay, so unfortunately the plus drive robot, I don't know if you guys remember, but remember the wire is absolutely dying. So right now I have a little rig. I took my headphone case and I put it on top of the wire. That way it smushes it down. It looks like, because our battery is dying, that is no longer sufficient. So, I'm gonna go look for another battery real quick. Y'all have some time to work on your wheel modules, which was supposed to be homework. I'm gonna be right back, everybody. Okay, so unfortunately, series of unfortunate events, I know, but unfortunately, we're just gonna go ahead and whoa, just put hers up. Ah, I see. Smart. Unfortunately, we're not gonna be using that. So what I'm gonna do is I'm gonna actually spend the next 15 minutes yapping about basically the basics of the SDK. That way, next session we can hit the ground running with our assignments. So I had a couple exercises that I wanted us to do with this robot, but it looks like those aren't working out because this robot is set to a very strange password that I do not know, nor does anybody else currently in the lab. So we're gonna get this password for next time. So basically, I'm gonna give you guys all the building blocks that you need to hit the ground running with your code next time. All right? So back up here, we talked about set power already. Very simple function. Now what I want you guys to remember is this code is operating like any other file in Java will, right? So code runs very fast, as we know, right? Line by line, pretty much instantly, right? And we cannot keep track of how fast it's happening. So this function is gonna run once I hit play on the robot. It's gonna go line by line, it's gonna do this, and then very fast it's gonna go here, and it's gonna complete that, again, very fast, before we even see it. And then it's gonna quit, right? Because this code ends at this line. So this program is actually going to look like it's doing nothing. Because if you think about it, it's going to set power to the motor at 0.5 and then immediately quit the program. And when the program quits, it cuts power to everything. So since it cuts power to that, this is pretty much doing nothing. So what we want to do is make this more in line with the timings that we perceive as humans. All right? So there's two ways we can do that. The first way is to make it reliant on something else to continue. So, for example, we have the wait for start method. You're gonna see this in pretty much every single piece of code that you use, and what this does is it stops the code right here and waits for you to hit play after you've already started your code. So there's two little play buttons. You first hit start and then play, or play and then start, or whatever, right? This basically waits for the second one before it continues with your code, right? Then there's other functions within this that you can also use. So for example, the while op mode is activated, or op mode is active. This function is going to return true or false based on whether or not you've stopped the code or not, right? Now, you may be thinking, why is that important? If I've stopped the code, it's going to stop what it's doing no matter what, right? But what I can do is I can put this in a while loop, right? And now what's going to happen is everything within this while loop is going to keep playing until I've stopped it manually, right? So this is kind of another way of making it wait on what we're doing in the real world, right? Everything in here is going to loop until I've stopped it. So now all that's going to happen is every single time this loops, it's going to set power to the motor at 0.5. Now, this is not the best piece of code because it sets power to the motor at 0.5 and then just keeps doing it for some reason. So if I was a motor, I'd be really annoyed right now because I'm at 0.5, what more do you want from me? But this is pretty much one way of syncing up our code with the real world, right? So that's what I kind of want you guys to be thinking about when you're making programs specifically for robotics. It's very different than making programs for just Java or to solve a math problem or anything like that, because we have to sync up to whatever everybody else is doing. Now, the way we make our code work with the real world, again, is with all of these different triggers. So we have wait for start, we have op mode is active, and then we also have the gamepads that we can play with, right? So the gamepad object is one that belongs to the linear op mode class. So I can reference it because, again, I'm inheriting everything from linear op mode. You can see there's gamepad 1 and gamepad 2. These driver hubs have enough ports to plug in multiple gamepads. So usually I have multiple drivers on the field. So gamepad 1 would reference the first gamepad, gamepad 2 would reference the other one. So I can say gamepad 1 dot, and then here I'll see everything that I want pulling up. And on the right here, you can actually see what each of those values is going to return. So for example, gamepad.a, that's going to return a Boolean. And that makes sense because A is a button. And since it's digital and we know it only has 2 values, we can map those values to true or false. So true is pressed, false is unpressed. Very simple. Now, I can use this Boolean to map things to the controller. So I could say if gamepad A motor dot set power to say 0.5. So now if I press A, my motor will start going in 0.5. Right? Very simple, very, I hope easy to understand, but all we're doing here is mapping our code to human functions. Now, if you think about this code, right? What's going to happen is it's going to run, remember we're running sequentially, so we're going to start at the first line, then run down here and wait for you to press the start button. Once you press the start button, it's going to continue, and then enter this while loop. Now while op mode is active, so pretty much it's going to run this until you stop it. So it's going to go down here, it's going to check if you pressed A. If you haven't, it's going to skip that, and then just check again because, again, while loop, so we're coming back to the top. Now, if you pressed A, the motor is going to start at 0.5 power, right? And then it's going to exit this. Now, say you stopped pressing A, right? Then you're going to come here, it's going to check you haven't been pressing A, then it's going to skip, but even though it's skipped, that doesn't mean the motor turned off, right? Remember, we set the power to 0.5, and we haven't set the power to anything else. So the power is going to stay at 0.5. So that's another concept I kind of want you all to understand. The power is going to stay at what you set until it's changed. So what I could do is, if I wanted to make it so that the motor only is running while I'm hitting A, I would say here, else motor dot set power 0.0. Pretty simple, right? So if I'm not pressing A, it's going to set the power to 0.0. If I press A, it's going to set the power to 0.5. Go ahead. Close. So wait for start is going to be that play button. So initialize, once you initialize, it's going to start from right here, right? And it's going to go on. Then it's going to wait for you to press the start button, and then it's going to continue from here. Now, while op mode is active, all that does is makes it so that my code keeps looping, right? So my op mode is active right after you hit wait for start, right? So it's playing right after you hit that start button. But I put that in so that it could keep looping, so that I could keep checking for different values. So for example here, I'm going to continue checking if you hit gamepad A. Right? Now, I know this stuff is very simple, and I'm doing a little bit of over explanation on it, but very important that we understand the foundation, so that when we get to things like PID, control loops, everything like that, everything is very solid, right? So I'm gonna keep hammering on this whole idea of think about the real world, right? Think about how it's going to interact when it's actually playing, right? So let's say I wanted to run based on a trigger, right? Triggers, we'll do gamepad 1.write trigger. And it'll always pull up everything that I need, which is so wonderful. So this is how you reference the right trigger, and this is returning to me a number, remember, between 0 and 1. So to operate on this, I could set it to a variable if I wanted. I could say double RT is equal to gamepad1.write trigger. And now RT stores whatever the value is. Now, a little redundant because, I already had it stored in gamepad1.write trigger, but this does make it so that I don't have to type out gamepad1.write trigger over and over again, right? And it's also quicker to reference RT since gamepad1.write trigger comes from a different class, right? So it's in a different file, so it's going to be harder for the code to retrieve it than something that comes from this file. So if I wanted to use this, I could set motor to the trigger. So RT. And this works, right? Because RT is always going to be a value between 0 and 1. And motor.setPower takes in any value from -1 to 1, which includes 0 to 1. Now, what if I wanted to set it to 1/2 right trigger and the other half left trigger, right? I have another 0 to 1 on the negative side, so I want to use another 0 to 1 input. So what I'm going to do is do the same thing that I did here. Instead, I'm going to make this LT for left trigger. I know I'm so clever. And now in here, I say LT. And now it's setting from 0 to 1, it's going to be the left trigger. Now that's the same thing that I had before, right? So I have to add a little more logic. So what I'm going to say is, if LT is greater than 0, it's going to do this. Now the reason I said that is because if LT is greater than 0, then I know it's being pressed, right? If it's returning to me a value that is greater than 0, then it's being pressed down intentionally. So I know I want to use LT as my metric, right? So if it's greater than 0, I'm going to set it to my motor. Else, I can set it to right trigger, but in this case, I'm going to make it negative. So now I have my motor's full range of motion, right? Everything greater than 0 is going to be set, or every time I'm pressing down the left trigger, it's going to be setting it to whatever the left trigger is, and that's always going to be positive, right? Then, if the left trigger is not being pressed, it's going to go ahead and go and set it to the negative of whatever the right trigger is. So right trigger is always going to be positive, and since I'm negating that, this value is always going to be negative. So basically all this does is now I'm holding my controller, I press right trigger, my motor's going to start going backwards. And it's going to go backwards depending on how far I'm pushing my right trigger. So if I push the right trigger halfway, it's going to go at 0.5 power. If I push it all the way, -1 power, right? Go ahead. Say that one more time? That's a great question. So if I wanted to set it so that both of my triggers were positive, and instead one is kind of controlling half the speed and the other one is controlling another half of the speed. So to do this, I could do some simple math. I would say motor dot set power, and here I want each one to represent half of what it actually is, right? So right trigger, I only want it to go half speed if I'm pushing it all the way. So I would say RT times 0.5. And I'm adding this to left trigger times 0.5. Now you can kind of see my logic if you do the math in your head. Let's say I'm pushing right trigger all the way and left trigger all the way, right? Then both of these values are going to return, and I'll put parentheses around it so you can kind of see it better. Both of these values are going to return 1, right? And then it's going to be multiplied by 0.5, so it'll be 0.5 on the left here, and then 0.5 on the right. So 0.5 plus 0.5 is 1, and that's full power. So with this code, if I push them both all the way down, full power. If I'm only holding one of them, that'll be 1 times 0.5 plus 0 times 0.5, which is 0.5. So it'll only run half power. So that's how you do it. Any other random miscellaneous questions about how I would run a motor in a very specific way? But no, it's not a good. Honestly, I thought that was a fun little exercise. That was nice. So we do have 3 minutes left, so I don't have enough time to cover encoders, so I'm going to go ahead and cover those at the beginning of next class. Now I know I yapped a lot this class, and we're gonna do a lot more application next class, all right? And hopefully I'll have a couple more bases ready for y'all so that we can split into groups and have more time on the laptop, more time, you know, actually interacting with the robot. One more note: Group 1, your robot is taken apart via me. So I don't know if you saw that before, but I took it apart because we had the mechanism wheels mounted wrong. So I didn't mention this before. It's honestly more of a building thing to know this, but there are 2 ways to mount mechanism wheels, right? You can either mount them in an X or in a diamond. And what I mean is the angle of the rollers needs to either be in an X or a diamond. So you have mechanism wheels and they have rollers at a 45-degree angle, right? So right here, you can kind of see the angle of the rollers is following that X shape, right? So then these 2 would be like that. Now the reason is that the way mechanism wheels work is it's a lot of canceling of force vectors. Don't worry, we're gonna have so much fun doing that later. But you have to have it in either this pattern or this pattern for them to work. And unfortunately it was not in either of those patterns, so I did take it apart. I was gonna replace the wheel, but then I realized we had no more spin cycles. So I'm gonna fix that on my own. Y'all don't have to worry about that. And we'll see if we're using this plus drive, depending on what the CAD class does. But I think it was a wonderful exercise building these bases. So proud of you all. I still owe group 2 prizes, and they'll get those shortly. I think that's all I have for you, actually. Yeah. So fantastic job today, everybody. Thank you for listening to me yap for pretty much the full hour. But I appreciate it. We're gonna get a lot more time next time.